5.8 inverses continued. So let's talk about some things you should know, or should know about, but you don't have to worry about them a lot, at least not yet this year. I do have to explain some things to you, so let's talk about the concept of a one-to-one function. Okay, so a one-to-one function would imply that every x value of the function, every x value has one, and that makes it a unique y value. Okay, that is the definition of a one-to-one function. And I'll give you let's look at two little graphs here, and let's see what that means graphically, because it's actually really easy to see graphically. And then we will tie it to inverses here in just a second. Okay, so let's say that this one is going to be x minus 3. So that cuts across at the y-axis at a negative 3, right? And it goes up 1 over 1, up 1 over 1, up 1 over 1. And so if you're at 3 over here, you get a nice straight line. So that would be a straight line that looks a lot like this. Okay. Alright. Let's make this one then y equals x squared minus 3. So that's a quadratic that also goes through 0, negative 3. And then it'll just go up 1 over 1. But then the next one, it goes up 1 over, what, 3, right? So, I mean over 1 and up. 1, 2, 3. And then you can mirror that over there. So that's a quadratic. And that looks then like this. Alright. Hopefully you have a slightly nicer graph than that, although that's not bad for me. Okay. So one-to-one. What does that mean? Well, every x here has a y value, right? But the y value that it has doesn't occur anywhere else. So if at 1 you're at a negative 2, then you won't find any negative 2's anywhere else. Whereas here, if I'm at 1, I'm at a negative 2, but if you were at a negative 1, you would also get a negative 2. So you get repeating y values, so that would be another way to sort of say it informally. So a one-to-one function, and you can test for that with what they call the horizontal line test. So for testing to see if it's a one-to-one function, you would draw a horizontal line, and if you only get one intersection on each horizontal line, then you say it's one-to-one. Okay, so it doesn't matter where you draw these horizontal lines, every single one of these only has one intersection. Okay, if I go then to the quadratic, almost every horizontal line I draw here, you see has two values, and that means that the y's aren't unique. So this y value occurs here as well. And that's what it means. Now it ties into inverse functions because a function has an inverse if it is one-to-one. Okay, so if it's not, so this one has an inverse. If it's not, then you don't get an inverse. And I want to show you that in the table real quick, so let's see. So at a negative 1, 0, and 1, what do we get? So at 0 we had a negative 3, at 1 we had a negative 2, and at negative 1 we had a negative 2. So the coordinates that we have are negative 1, negative 2, 0, negative 3, and 1, negative 2. Let's say we find the inverse for that, right? So that means you swap your x's and y's. So then at a negative 2 you get a negative 1, at 0 you get a negative 3, and at a negative 2 you get a positive 1. And then here you have the problem. At a negative 2, sometimes you're a negative 1, and sometimes you are worth 1. So this is not a function, right? Because a function is not allowed to have repeating x values. So that's what you get, okay? I don't deal with this a lot with you guys in terms of problems, but you do have a couple of these on your next problem set, and you need to be able to talk about this a little bit, but mostly informally. All right. So let's look at domain and range for inverses. So let's say that I have an original function and it is 2, 1, 3, 4, and 4, 7. Okay, so that's the whole function. Well, the domain for this function would be 2, 3, and 4. And the range would be the values in the y, so 1, 4, and 7. Okay, let's look at our inverse. So for the inverse, we can just swap x's and y's, right? So 2, 1 becomes 1, 2. That becomes 4, 3. And this becomes 7, 4. So that domain would be 1, 4, and 7. So those are the only x values you get to use. And then the range for the inverse would be 2, 3, and 4. Those are the only y values that you get. Now look at this. The domain for the original is the range of the inverse. So the domain from the original is going to be the range for the inverse. And the other way around, the range of the original is the domain of the inverse. Okay, so the range of the original is the domain of the inverse. See that then in red, so consistent. And that does go both ways. So the domain of the inverse is the range of the original, and the range of the inverse is the domain of the original. Now you may be wondering, why is this important? You know, lately we've been doing questions with domain and range, and it's usually based on a picture, and sometimes you don't have pictures. So to find the range, for example, for 1 over x minus 5 plus 3, or let's make it a little more difficult, negative 4. Okay. Now some of you can look at this and you know exactly what the domain and the range for this would be. But sometimes it's just easier to actually just find the inverse, and then if you look at the domain for the inverse, then you can tie that back to the range of the original. Now that is something we're not really going to do this year, but it's something you should be aware of. Definitely this part, domain original, range inverse, and the range of the original is the domain of the inverse. It literally has to do with what? You are swapping x and y, right? Okay, so if x is the domain and y is the range, and when you swap it, then you're swapping domains and ranges as well. Alright, let's look at the last thing we need to look at is graphically speaking a little bit. So what happens graphically speaking? So here's 3x minus 1. So 3x minus 1 will look like this. It's a negative intercept, negative 1 for the intercept, and then up 1, 2, 3 over 1. Okay, and I can do the same thing one more time, and the same thing one more time this way. And so it looks like this, right? And I'm just going to sort of dot it, because I get better lines that way. Okay, let's find the inverse for that. So this is the y, and then that's the x. Swap your x's and y's. Solve for y. So the inverse would be y equals x plus 1 divided by 3. Now that's a little harder to graph because it's not in slope-intercept form, but you can pick some values that are easy to work with. For example, at a negative 1, you get 0 on the top. So at a negative 1, you should be at 0, right? Let's do that in blue. So at a negative 1, you're at 0. And then if you pick a 2 here, 2 plus 1 is 3, and 3 divided by 3 is 1. So if you're at 2, you're at 1. And you can then clearly see your slope, for example, it's up 1 over 3. So up 1 over 3, you should have another dot, for example, here. Okay, so that's at 5. You look to be at 2. 5 plus 1 is 6. Divided by 3 is 2. So it's working, alright? Okay, so I'm going to do the same thing over here. Actually, I'll put one more dot over here. So, okay. Now we talked about this a little bit, but the other day we only had straight lines that seemed to be running parallel, so I definitely wanted to make sure that today you saw something that has two straight lines that intersect. Is this, could you see that this function has that as its inverse? Well, you can see it and then you can check it. And the way that you do that, again, is if you use the line y equals x. So the line y equals x goes through all these values where the x's and y's are the same. So here, here, there, there, there. Now look where these two intersect. That looks to be the spot where the y's and the x's are the same. Here, 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 and here. And so I'm not really good at this graphically. I just struggle with that a little bit. But it certainly seems to work that you can mirror this point. So this point mirrors straight across here. And this point mirrors straight across in here. And these two mirror straight across this line into each other and here as well. Okay? So that's what it looked like over there. A little more interesting is actually when you do it with hyperbolics, at least in my opinion. So this is a hyperbolic function. So it has a horizontal asymptote at 2. Right? And since x can't be 0 here, then the vertical asymptote is that x is equal to 0. So that's this line. And see, the top one is worth 1. It's positive, so it goes through this dot and this dot. So there is the original function. And I guess I switched my colors again, so in this one, I don't like that one, sorry. Alright. Okay, so let's find an inverse for this. That's good practice too. So swap your x's and y's. So this was your y, so that should be then your x. So that's 1 over y plus 2. Move the 2 to the other side. X minus 2 is 1 over y. Think of this as a cross product, so these two can just swap. So you get y equals 1 over x minus 2. Well, that is still a hyperbolic. It has a plus 0 over here, in case you're curious about the structure. So it has slightly different asymptotes. Here, the horizontal asymptote is at y equals 0. And the vertical asymptote is at x equals 2, because x minus 2 cannot equal 0, so x can't equal 2. Well, compare these values, y equals 0 and x equals 2, with y equals 2 and x equals 0. So the other one had these two, y equals 2 and x equals 0. So this is the original. Right? And hopefully you're seeing a pattern here. You literally swap x's and y's, right? So if the original has a y equals 2 horizontal asymptote, then x equals 2 is the vertical asymptote for the other function, for the inverse. And you can use that fact sometimes, but here we can just sort of look at it and see that that is what happens. So that's where this asymptote goes, x equals 2. This one has a horizontal asymptote of 0, so it would run here. So here's your new origin intersection, so then this dot must be on it because it's a positive one, right? And then over here this dot is on there. And so your graph looks like this. And here your graph looks like this, okay? Graphically, or I mean I can try to draw the line y equals x, it's a lot harder to see here. I do want to point out, and it's a little bit easier to see on this one than this one. Here's the intersection of the inverse and the original. And look, they're both almost at 3, right? So that used to be, that's, the coordinates there are just under 3, so it could be like 2.9, comma 2.9. And again, the intersection occurs, so the original and the inverse, they intersect at points on the line, that will be with a t, on the line y equals x, because they only intersect where the x's and y's are the same, because when you swap them you get the same point back. Otherwise you should, clearly get a different point. Okay, thanks.